Very well. We are now getting to the final section of this chapter, which we will now close out. Let's do a brief review and see where we've been. Section 1, we started looking at our two substances, specifically chlorofluorocarbons and ozone, and how they interact, or at least there was an idea of how they interacted. That introduced us to the idea of science. Then we got into chemistry and matter, which got us into the chemistry, which was taking a look at these substances, how they were made, and how they react with each other, which is what chemistry is all about. It's the study of matter and the changes that it undergoes. We then took a big look at the scientific method. Very important piece, very big thing to learn. It's not just that you want to know the steps, but you need to develop a thought process along this. Lastly, we're now going to take a look at what scientific methods do for us in doing scientific research. So, we want to be able to look at what is pure research, applied research, and talk about technology. We are also going to do a little bit of a look at safety. Laboratory safety is going to be coming in here, but on Tuesday, we're going to spend the whole block talking about lab safety, and there's a whole demonstration and discussion that'll go on there. A review piece, you've heard a lot about the word synthetic. A synthetic is actually something that is simply man-made and does not necessarily occur in nature. That doesn't mean that it doesn't occur. For example, one of the big things that's going on these days we read about is the differences between something organic and something non-organic. Organic vegetable versus a non-organic vegetable. What's the big difference? Is there a difference? One of the things that they're finding, it's not that the vegetable is not organic. It's just how it's grown. So organic has now taken this whole new term and it's morphed into how you grow things. Organic farming typically is farming where pesticides are kept to a minimum, and if they're used at all, they use natural pesticides, of which there are quite a number. Synthetic pesticides. Synthetic pesticides are kept to are man-made. They're kept to a minimum. Ammonia actually is a good example of something that became a man-made fertilizer. Even though it occurs naturally, it does. It occurs in nature. You actually excrete it. It's part of our waste as human beings. It's part of most animal waste. And yet, synthetically, it got made by, if you remember, I was talking about Ernst Solvay the last time. In his Solvay process actually generated vast amounts of ammonia and helped him create a boon in refining farming, especially in Europe. Now we want to talk about what's organic and what's not organic and whether it's better to buy that or not. A rule of thumb. We're actually going to look at a report on a couple of studies, and we will talk about this critically in one of our classes coming up. One of the things to remember about things that are grown synthetically. Corn is a great example. I can grow corn. It used to be you grew one corn crop every year, but because of man-made pesticides, man-made ways of fertilizing, I can actually grow corn faster, and I can grow maybe 3 crops of corn in a year instead of my 1. What happens because of that? Well, a lot of times the soil doesn't necessarily have the time to regenerate all of the vitamins that you usually get in corn. So there's the possibility that my 3rd corn crop may not have as many vitamins in it or have them to the amount that my original corn crop did. Or if I compare it to an organic crop, which is a crop that's grown regularly for its whole year in a regular normal cycle, that one might have more vitamins or a larger amount. It's not always the case, but it's possibly the case. A theory that goes to that, a scientific theory, because it's been studied and looked at, is the idea of continuously using that soil several times a year as opposed to the one time a year depletes the soil of the nutrients that you would find in the vegetables. Also, there's going to be some vitamins that take time to develop and get into fruits and vegetables, and that may not necessarily show up. It doesn't make it bad, okay, but it does happen. So, pure and applied research, that's what we want to be talking about. That's where this kind of scientific research and stuff comes in. So the idea of looking at what is organic, what's unorganic, that's a bit pertinent. So again, we'll have a discussion about that article. We'll bring that in. I'll put that up for a piece. We'll spend a little bit of time on it, maybe tomorrow, maybe on Friday. Okay, so some scientific investigations result in development of technology that can improve our lives and the world around us. Okay, types of investigations. Pure research. Pure research is the research that actually you, in a sense, are doing. You're doing research. What are you trying to do? You're trying to gain knowledge. What knowledge are you gaining? Knowledge of chemistry. So you're conducting, in a sense, pure research. You're gaining knowledge for the sake of knowledge. You're not going to do anything with it right now. You're gaining it to get your base, to establish your base. You want to know. Okay, so in a sense, you're conducting pure research. Applied research is research undertaken to solve a specific problem. In applied research, what ends up happening is you often come into chance discoveries that occur when these scientists obtain results far different than what they were applying for. All right, so a sidebar before we get into all of this with research. Of course, what it means for you with research, you're going to conduct experiments in the lab. So the first thing that you need to remember, we're going to get into the safety contract. We'll break all of that down on Tuesday, your first lab day. But you're responsible for your safety and the safety of others around you. On page 19 of your textbook, you're going to see a list of safety rules. The rules that you really need to follow will be the ones in your safety contract. You're going to have a lab safety test the following lab cycle in which you must get a 100. You cannot miss a question. And that will be based on your lab contract. Okay, let's take a look at what we're going to do with the CFCs. Pure research, applied research. All right, so we want to do applied research. Why? Because they want to take a look at what CFCs do in the environment. So in that research, they found that CFCs reacted with ozone, including formaldehyde. In 1987, it was demonstrated that it was such a bad extent of CFCs with the ozone layer could be so detrimental, there was an agreement made that consumption of CFCs will cease. Now, from a data analysis standpoint, I want you to take a look at this graph. Notice how this blue line, which is the global consumption of chlorofluorocarbons, is all the way up. You read the right-hand scale for it. It's around 1,100 metric tons. Okay, you need to read the right-hand label to see how it's labeled. That's 1,100 metric tons are produced in a year. By the year 2000, that drops below 200 metric tons. However, even though they stopped, and if you notice, even before 1990, by the time 1990 around, they had already dropped from 1,100 metric tons to around 700. So they had already significantly decreased the amount. Not quite in half, but they were very, very close. What happened even though they did this? Look at the level of CFC 12 and CFC 11. As you can see, it continued to go up. Keep these things in mind, both in the area of chemistry and what often happens with chemicals. Stopping a chemical reaction or stopping chemicals from occurring or continuing in whatever processes they're doing isn't like stopping a car where you can slam on the brakes and stop right away. when you discontinue something, oftentimes in chemical situations, the chemistry is going to continue because the particles are still out there. Just because we stopped consumption of CFCs doesn't mean CFCs weren't produced and already out in the atmosphere. They were. So of course their levels continued to rise. But the levels didn't rise as high as they would have had we continued our consumption. Think about that when you're having a discussion with someone at the table, perhaps about global warming, and the fruitlessness or the situations with CO2, carbon dioxide, and other global warming gases, and how we might combat that. Okay, what ends up happening is we have now learned that every spring over the Antarctic, there is a thinning of the ozone layer. At one point, it was as large as France. It is now much, much smaller. I'm not sure the actual size. I'll try to look that up and let you know. But it has definitely gotten much, much smaller at this point in time. Okay, so what does all this demonstrate? What is this discussion of the CFCs and bringing all this about, having you look up and talk about formaldehyde? What does all this mean? What does it demonstrate? Well, it demonstrates that chemistry brings you benefits. Benefits in that you get to find out about what's going on with nature, and benefits that if you're acting quick enough, as we did with the 87 protocol, you can reverse something that could be detrimental to the Earth and the population. Keep in mind, this is the only planet that we know of that has human life. And as far as we can tell, there's not another planet around within the lifetime of a human being that we could get to if we botch it and we have to get off this planet because we can't live here anymore. The next hospitable planet, closest possible, is about 200 light years away, which means if we were traveling at the speed of light, it would still take us 200 years to get there. None of us would survive the journey. Okay? So those are things you've got to think about. Benefits of chemistry. We solve real problems. Ozone depletion is certainly the big one. Finding cures for diseases. Fleming and his penicillin. Probably the most famous case of a chance encounter. Reducing the weight for cars. There is a law out that says miles per gallon for cars have to get to 35, I believe, by 2015, which is only a few years from now. So 35 miles a gallon. So that means the cars have to find ways to make cars lighter. They've been doing that. Okay, so accidental discoveries like penicillin, what do we call them? Chance discoveries. What kind of research solves specific problems? Applied research. Okay? And that's it. That is section 4, and that is our first chapter. So now we can really start thinking like chemists, and we'll head over to chapter 2 shortly and take a look at data analysis.